Thank you all for attending the 2014 Fall Design Review of ISUAV. My name is Justin Mosier, and I'm a senior in chemical engineering.
I'm Louis Deach, and I'm a aerospace engineer, senior.
I'm Zachary Lammy, and I'm a junior in aerospace engineering.
I'm Jaime Greza, I'm a senior in aerospace engineering.
I'm Corey Preston, I'm a sophomore in aerospace engineering.
I'm Aiden Moffett, I'm a junior in aerospace engineering. I'm Colton Dahlm, I'm a senior in aerospace engineering.
I'm Akash Gadrin, and I'm a sophomore in aerospace engineering.
I'm Ben Getson, and I'm a sophomore in aerospace engineering.
I'm Ryan Sanders, I'm a senior in aerospace engineering.
If we're engineering sophomore.
I'm Morgan Rocha, I'm a senior in aerospace engineering.
And I'm Alex Woodhall, I'm a junior in aerospace engineering.
ISUAV is a multidisciplinary, student-driven group project dedicated to designing, manufacturing, and operating low-cost, small unmanned aerial vehicles capable of performing a variety of civil applications. Here is the roadmap for this presentation. I'll begin with the background. In December of 2004, NASA's Dryden Flight Research Center released a document that was an assessment of the civil applications for uninhabited aerial vehicles. This document included a list of barriers to entry for UAVs. We focus on 3 of these: affordability, payload flexibility, and operator training issues. ISUAV, formerly known as Cydrone, began with X1. X1 was a commercially off-the-shelf airframe that was affordable, but it was not easy to use and did not provide any payload flexibility. The next iteration, X2, was affordable, it was easy to use, but it also did not provide payload flexibility. Our current iteration, X3, is an in-house designed and manufactured airframe that is affordable, easy to use, and provides ample payload flexibility. What makes X3 so great is we have taken all of the critical electronic parts that are critical to flight and put them inside of what we call the Flight Critical Systems box. Right next to the Flight Critical Systems box is the module box. And this box is empty, which means you can put whatever you want inside of it, and it will interface perfectly with the Flight Critical Systems box. With this module box, we've effectively made a plug-and-play device. I'll now hand it over to Louis, who'll be talking about X3A.
All right, so what we'd like you to know is that we are pleased to inform you that we are done manufacturing the X3A model. And we're ready for the testing phase. So, unfortunately, we ran into an issue. We had to strengthen the aft of the aircraft with fiberglass. And so we effectively have a center of gravity that is 4/5 of the chord at the trailing edge. And what we want is the predicted CG, which is the quarter chord. And what we're doing to remedy it is exploring different payload configurations.
Our current iteration of Cydrone is X3B. We removed the rigid structure from X3A because it weighed a lot and didn't provide as much structure as we were hoping. We also were able to change the orientation of the FCS and module so then we could optimize the module size.
So things we've been doing so far this semester include improving the accuracy of our SolidWorks designs. We've just been adding in some little things that are going to make our models more accurate to what the final production is going to look like. We've also been working to increase the manufacturability of our designs. We talked to some of the guys in the Boyd lab about what can and cannot be done with the CNC machines. So we're going to make small changes to help with that. And we are very close to the final finalization of our design and should be able to begin the manufacturing process soon.
We are starting to use more realistic Star CCM models that will provide for more accurate results. These include having all of the inlets, the inner flow, also includes having stuff such as the servos and control horns. We're doing 1,000 plus iterations for accuracy, and we now feel we can accurately use Star CCM to prove our new designs.
In order to get better simulation in our CFD, we decided to move around a little bit of our meshing. This semester we are meshing the half body of the airplane, and we are trying to increase the lift and drag with this mesh. We are running into a few issues on the trailing edge of the wing, and we're getting flow separation. And once we get that fixed, we're going to have better simulation when we run our CFD.
We're also using Star CCM to evaluate a new side inlet. This will help us determine the most efficient way to cool our electronics without removing so much material that we begin to compromise our structural integrity. Over the course of 3 simulations, with air inlets varying in shape and size, we have found that despite this, the airflow of all 3 inlets is largely the same. We've also been experimenting with side scoops that protrude out of the fuselage surface in comparison to the inlets we previously worked on that were flush with the surface. As you can see with some of the results, the velocity results on the left, the air propagates fairly well, but we still want to experiment with the size, shape, and position of these scoops to get better airflow throughout the entire inside of the fuselage.
So the X3A originally weighed approximately 2.5 kilograms, but on removing the redundant 3D printed rigid structure, we were able to cut down the weight by approximately 427 grams. Therefore, the X3B now only weighs approximately 2 kilograms. This reduction in weight is crucial as it allows us to increase the payload. Yeah. So we've also done some physical testing regarding the thickness of the foam, especially at the back part of the aircraft. As now, since we removed the 3D printed rigid structure, we did not want to compromise on the structural stability of the aircraft. Therefore, the part of the aircraft which houses the engine was stress tested. The engine, which originally provides a thrust of 6 kilograms, was stress tested, and it survived the stress test of about 7.5 kilograms. Then this test proved that we did not need the 3D printed rigid structure.
We are also looking into using different wing designs. Our previous designs for the wings in X3A and X3B have been limited by our manufacturing methods with the hot wire. But we are CNCing our wings now, so we're going to use Star CCM to optimize designs to decrease drag. And now to Ben with module development.
As we've begun flight testing with our X2C airframe this semester, we went back through and we started refamiliarizing ourselves with our mission planner software that we used to run, or will use to run semi-autonomous modes. We've been focusing on 3 different areas of the mission planner software. We've been looking at the different autopilot settings available to us through the software, and also our data capture modes that we can use in conjunction with that. We've also been looking to streamline our specific mission plans, so we know exactly what we're going to do when we're trying to do it. And we've also been looking at the different flight modes available through the mission planner software, so that we can efficiently transition between the different flight modes through the software.
Myself and the rest of the flight test group have been working on doing some ground testings on X2C for the first part of the semester. The reason we've been performing these ground tests are to make sure that our critical systems, such as the location finder or the auto stabilization systems, work well on the ground before we launch the plane in the air and cut out the hard way. Excuse me. Typical testing configuration consists of a tripod on which we have a receiver that communicates back and forth with the FPV or first-person view system that's on the plane. We also have a transmitter and a receiver that communicates with the GPS system and the autopilot system that is on the plane. We always make sure that our motor is unplugged, mainly for safety reasons while on the ground or while the airplane's in one of our hands, especially when doing any of the autopilot tests, such as the waypoint tracking. We also bring 2 computers with us, one that hooks up to the FPV system receiver so we can see what the plane sees, and the other computer so that we can run Mission Planner and we can simultaneously communicate with the planes and programs back and forth while we're either on the ground or while we're flying. So as I've kind of mentioned, some of the systems we've tested the FPV system, we have tested the GPS location finding system, and we have tested the autopilot auto stabilization and the autopilot waypoint tracker, as well as with just the normal control surfaces of the plane. The results so far have been very promising. The FPV system works very well and has an excellent range. We've tested in the HAL parking lot, and I've been able to carry the plane all the way to the opposite end of the parking lot while our tripod is set up at the opposite end. And even with cars in the way, it still has excellent connection. The GPS location finding system works very well. Looking at the mission planner while I'm holding the plane, we're able to narrow down the location just to a patch of concrete. The autopilot auto stabilization system works very well. It's hard to simulate the motion of a plane while I'm holding it versus when it would be flying. So while I pitch the plane up or down or roll it left or right, the control surfaces seem to react and level the plane out. 1 point for improvement would be the waypoint tracking system. While on the ground and myself holding the airplane, we've had a difficult time getting the waypoint tracking system to work. So we hope with further flight testing, we can be able to fix this issue.
We continued working on the kill switch. During the installation of the kill switch in the test bed X2C, we found some major connection issues. The connection would fail if it was pulled or twisted from the both ends of output and input. Once this issue was fixed, we reran ground tests and found the same range of 0.2 miles.
Because Ryan and I are both AMA pilots and also members of the Central Iowa Air Monitors, we were deemed pilots of ISUAV. Last week, we took X2C out to smaller fields just southeast of town for some flight tests. We flew like a basic RC airplane just to familiarize ourselves with the aircraft and the controls. As you can see from the flight test matrix, the flight was a success. We're currently working with Matt and M2I to plan a future test where we would like to test the different capabilities of the mission planner with the main goal of testing the search and rescue app, which David and Justin will elaborate on.
Last semester, we worked on proving the feasibility of an infrared-based search and rescue module. While it answered the question, is this possible using consumer hardware, it was unreliable, difficult to manage, and had basically no support for mobile devices. In addition, browser support for Google Earth, which it relied heavily upon, is being dropped soon. So this semester, we're redesigning the server and client programs using modern web standards. This will provide multiple benefits. First, it will allow us to create attractive, easier to use interfaces, which will promote adoption. By creating a modular, scalable design, it allows us to have a framework that we can reuse in future modules that require a connection with the ground. And lastly, it will provide more maintainable code for future ISU UAV members to expand upon.
All right, a lot of work has been going on, or has happened over the summer and this semester on our search and rescue application. We are 99% sure that the orientation calculations are correct now. We also realized that we would have to turn on the app prior to putting it into the airplane and then not be able to stop it until after we retrieve the airplane and take it apart. So what we decided to do was add functionality so that we could start and stop the app wirelessly over Bluetooth. And we can now actually estimate the bright spot location without communicating with the server. And this is great for when there is no mobile connection. And now I'd like to take a few minutes to just describe exactly how this search and rescue application works. So here's a photo I took a couple of days ago. Hopefully you can notice the green dot that's in the lower left-hand corner. It's hovering over a person who is wearing a bright red and orange jacket. What we're essentially doing, the best way to conceptualize this, is we're putting this photo into Google Earth. And then we're putting the cursor right over the green dot, clicking, and it's dropping a pin right where the cursor is. And that pin knows exactly the GPS coordinates. And so it just tells us right where that bright spot is. And we don't actually have to go there to figure out what the GPS coordinates are. But we realize that that's inefficient because we don't need to put an entire photo, which is maybe 5 megabytes of data, into Google Earth or whatever system that we use. We only need a vector. And so the way this vector works is you could say, I'm standing here, I can see something bright over there, I don't know where there is, but I know it's over there. And so we take that vector, we run it through Google Earth, the same exact way as you have the photo in there, and then click on the screen and it'll tell you the GPS coordinates of the bright spot. And now I'm gonna explain exactly how we get the vector. So here's the photo, I'll pull up my phone here. Using some physical parameters of the device that we're using, which is the horizontal and vertical field of view, we can then figure out, based on the deviation from the, like, if the point was directly in the center, we can figure out like how many degrees off it is using this horizontal and vertical field of view. And then now we have the vector in the reference frame of the device, and we need to get that reference frame in the reference frame of the Earth. So what we use some quaternion math, which avoids gimbal lock, so it's very confusing, and I won't go into it, but we're able to get that vector into the reference frame of the Earth, and we run that into the server with the latitude, longitude, altitude in a JSON file, and we're able to process this information without using any photos. Here are the actual results of that photo that I just showed. The green arrow is pointing to the actual location. The red arrow is to the estimated location, and this is without using the server. So there is some error, and probably all this error, really. I'm confident that all this error is contributed to the fact that we haven't calculated the field of view angles for iPhone 6 Plus, which is the device I use. We have it for iPhone 5, so it's a little off right now, but we're going to fix that real soon. Now for the outlook. Now that we've completed manufacturing of X3A, we'd like to begin flight tests. X3B is nearing the finish line with its design, so we're going to begin manufacturing. And by the end of this academic year, we would like to have a successful search and rescue mission. Here's our budget. We'd like to thank Boeing, Rockwell Collins, M2I, DIY Drones, the Aerospace Department, and of course, Matt. And at this time, we will be taking questions.